Hello, I'm Jay Shah, and I'm a graduate student at Texas A&M University. Thank you for joining me today as I present my work on robot adaptation under operator cognitive fatigue using reinforcement learning. We all know the emergence of human-robot collaboration due to its ability to leverage the decision-making capabilities of the human and accuracy, precision, and durability of the robot. As a result, collaborative robotics is being applied to various fields such as manufacturing, emergency rescue, and medical applications. However, these applications require high time on task, which can lead to cognitive fatigue in the human, since they have a limited supply of cognitive abilities which tend to decline over increasing time on task. These cognitive fatigue leads to task performance declination, increased task difficulty perception, situation awareness issues, trust issues, and problems with technology acceptance. Therefore, it is imperative that cognitive fatigue be considered while designing a human-robot collaboration scenario. Hence, the problem statement is the following. To develop a robot adaptation model that can be applied when the human is cognitively fatigued, with two goals in mind: improve task performance under fatigue state and mitigate fatigue. This is done via reinforcement learning. In reinforcement learning, the environment provides states to the robot according to which the robot takes an action, and in turn, the environment gives rewards to the robot. With sufficiently high number of such interactions, the robot learns to act in a manner we desire. The robot adaptation model is presented with the use case of robot surface polishing operation, in which the human operator is supposed to control the robot using a joystick and navigate along the S-shaped trajectory drawn on the metal plate. The goal of the task is to trace the trajectory as accurately as possible while maintaining sufficient contact force. Now we define the parameters of the reinforcement learning model, which has the structure of a Markov decision process. State S is the discretized location of the robot along the S-shaped trajectory, which is divided into 5 segments or events. There are 3 actions. Action A is manual, which means the robot will move according to the operator's command, and there will be no assistance provided by the robot. Action B is assistance without alerts, in which the robot would provide some assistance to the operator but would not communicate it to the operator. Action C is assistance with alerts. Now, these assistance features are event specific. For example, if the user is navigating the robot through event 1, the assistance would be to automatically correct the deviation caused by operator. But if the robot is in event 2, then the assistance would be to make the U-turn automatically to provide relief to the human momentarily. The alerts are contextual audio and visual alerts that are assistance specific. The last parameter to be defined is reward. Reward is based on fatigue quantification, which is done using a binary classification support vector machine. ECG signals within a sliding window of 1 minute is fed to the SVM, and prediction confidence of the model for being in the fatigued state is used as the degree of fatigue. Hence, the reward is defined as the difference of prediction confidence before and after taking a particular action. Since fatigue is a long-term quantity, 225 seconds of data is taken for calculating rewards. Finally, the MDP is solved using Q-learning. The update equation is mentioned here, which has the learning rate and temporal difference error shown. This is based on finding the fixed point of the Bellman operator. At convergence, TD error goes to 0 with the right learning rate. Certain implementation issues are also mentioned and solved here. First issue is exploration versus exploitation, which is a classic reinforcement learning problem. Another issue is time lag of 225 seconds in reward calculation, as mentioned earlier. This is solved by setting exploration trials and then using that data to perform offline training. Another issue is that the rewards are noisy since they are based on a machine learning model. This is solved by normalizing the prediction confidence of the SVM to draw a bound on reward signals calculated thereafter. The experimental protocol was to bring in participants and train them on the task and perform bioinstrumentation. Then they went through an hour of two-back fatigue manipulation task to induce cognitive fatigue. Following this, they were given a block of baseline trials, which consists of 6 trials. A baseline trial is a trial in which actions for all events of the trajectory are the same. Then, the participants were given 40 exploration trials whose data was used to derive optimal policies for each user. After that, they were given another block of 20 minutes of fatigue manipulation, and after that, they were given validation trials to record the data for the optimal trials. And the results are presented using cognitive fatigue measures and task performance measures. Literature shows that the higher value of RMSSD corresponds to high fatigue. This means that when optimal trials were given, there was significant cognitive fatigue recovery. With mean heart rate, low value corresponds to high fatigue. This also verifies that during optimal trials, cognitive fatigue recovery was significant. Looking at the fatigue perceptions of the participants, it shows that the optimal trials were able to relieve them of the fatigue they experienced earlier. Task performance metrics are captured using errors in trajectory tracking and trial completion times. It can be seen that both errors and trial time are low for the optimal trials, which shows that the optimal trials also helped in improving performance. So to finally summarize, we present a framework for robot adaptation under operator fatigue state to aid cognitive fatigue recovery and improve task performance. This recovery is done while actively being on the task without any breaks. The trials also improved performance, and most importantly, majority participants liked the optimal trials and readily accepted them.